So far in this course, we've taken a look at 3D geometry, how to render that geometry on a screen or image, and the virtual light simulations we can use to illuminate surfaces. With these prerequisites out of the way, we can now examine materials and see how the color of a surface point on an object can be determined by taking into account light and the properties of the surface material. So formally, we call these materials bidirectional reflectance distribution functions, or BRDFs. And the reason they are called this is that they consider light from an incoming direction. So let's just say, actually, let's just label this line right here as our surface, and let's take a look at that light as an incoming, as a vector, really, just showing which direction the light is coming from, right? So a BRDF, a bidirectional reflectance distribution function, considers light from an incoming direction and determines how much of that light is reflected off a surface at a certain point. And it will be reflected off in the view direction, right? So let's just call this the view direction or view vector. And this is basically the direction from which we are observing the surface point. We could kind of imagine our camera being at this location, right? And we're looking at the surface point from this point of view. All right, so this is what a BRDF allows us to do. It allows us to figure out exactly what this surface point should look like when we observe this from a camera, right? How bright should it be? How should it be illuminated? What color should it be based on the properties of the surface itself? Does it absorb a lot of light? Does it reflect a lot of light? And there's other things that can happen here too, right? We could even be transmitting a certain amount of light. We'll talk about that a bit later on. Light could be entering the surface of the object and scattering around a little bit and then exiting somewhere else. Again, we'll bring this up a bit later on in the lecture. But in a general sense, this is all we mean when we're talking about a BRDF. Now, to understand how BRDFs work, let's consider a very simple material model and break it down into individual shading components that we can directly observe, or at least imagine, in the real world. So let's start with ambient shading. This is a very simple type of shading that we can simulate in that it does not take into account the position or rotation of any light source in the scene, right? Remember, back to the lecture on lighting, the ambient light source that we talked about. Its position or rotation does not matter here, and it essentially just uniformly illuminates surfaces in the scene, right? As a quick example of this, we can actually just use the Eevee renderer in Blender. Really convenient just to get to take a look at some 3D objects and see how different lighting interacts with them. Let's just simulate the effect of ambient lighting just by increasing and decreasing the world light intensity. And we can see in a very basic sense here the effect of ambient lighting. Okay, so it's just a general universal illumination on every object in the scene. Doesn't matter what other light sources there are here. I happen to have a point light source just up above this sphere right here. But ambient lighting is going to increase or decrease the brightness of every surface. Overall, right? So that's just an example of what we're trying to simulate here. And we could calculate our ambient shading intensity with a very simple equation here. Let's set A, which will be our ambient, our ambient energy. Let's set A equal to just the product of two values, and that'll be our ambient reflection coefficient. So I'm going to call that K sub A times the ambient light intensity, and I'll call that I sub A, right? So just a coefficient for ambient reflection, and we could think of that as the color of the ambient light, and of course the intensity of the ambient light. Pretty straightforward. That's just how bright this universal illumination actually is. So a very simple equation, and we'll be using this formula to introduce an ambient shading term into just a simple shading model that we're building up to here. All right, next let's talk about diffuse shading. So with diffuse shading or diffuse reflection, what we're doing here is receiving light from a light source. So we can draw that out as we have our surface, and we're observing a certain surface point, and there's an incoming light direction. And what we're doing here is observing the type of reflection that is reflected off in all directions. So the reflected light is going to look a little bit like this. This is distinctly different from more mirror-like reflections. That's an entirely different part of our shading model. So for the time being, we're only talking about light that is reflected off in all directions like this. And of course, as we saw with the original diagram I drew, from this side view, we will be observing this surface point from a certain direction. So it'll just be whatever light enters the camera from this certain point of view that we are observing here. But nevertheless, it is important to understand that diffuse reflections do get scattered off in all directions, kind of in a hemisphere-like shape around that surface point. And again, back in Blender here, just using the Eevee renderer to get a quick preview of some lighting here, we can take a look at the effects of diffuse lighting. So I have this sphere, I have a single point light source just directly above it, and we can see this sort of lighting that you see here. There's no sharp reflections anywhere. It's just very smooth lighting. We call this diffuse lighting. This is what it looks like. And what we want to observe here, specifically what we want to point out, is the fact that the part of the object that is illuminated doesn't change depending on the view direction. So remember, with diffuse lighting, light is reflected in kind of in this hemisphere shape around a surface point. It's reflected in all directions over that hemisphere. So doesn't matter what view direction we define here. It doesn't matter from what angle we view the object. The diffuse lighting is going to appear to be static, if you will. It's going to illuminate the same parts of the object, right? We can put this light wherever we want, but the lighting is going to stay there. It might seem a little bit weird that I'm making such a big deal about this, but we're going to see a distinct difference between diffuse lighting and specular lighting. It's called where we're dealing with like perfect reflections off of the object itself. And we're going to see that specular reflections actually move around and they appear on different parts of the object when we move the camera. So I'm just pointing out here that with diffuse reflections, the lighting is what it is. It doesn't move. It doesn't appear on different parts of the object. It just stays put, and no matter what angle we view the object from. So in order to calculate diffuse shading, we could write out an equation like this. All right, we're going to say, in this case, D, which is going to be our diffuse light intensity or our diffuse shading, is going to be equal to, again, we're going to bring in these two coefficients similar to what we saw with ambient shading, the product of a diffuse reflection coefficient, so I'll call this KD, multiplied by ID, right? So this will be our diffuse light intensity. But we need to bring in another component here as well. And this is where things start to get a little bit interesting. We are going to bring in the dot product of two vectors. Specifically, we are going to bring in the dot product of the polygon's normal vector. So actually, I'll draw that in here. Hopefully, it's still not too confusing what this diagram is all about. But yeah, so we're going to bring in the surface's normal vector, and we're going to take the dot product between that and the incoming light vector. So we'll put that right in there. All right, so why are we multiplying this product of diffuse coefficient and diffuse light intensity? Why are we multiplying that by the dot product of the normal vector and the incoming light vector? Well, if we just draw out another little example here and kind of think through what the dot product gives us, what that scalar product between two vectors actually means, we can start to see how this makes sense, right? Let's just consider a few scenarios here, right? Here's our surface. Here's our let's start with our light source actually directly overhead, and then we can just include the surface's normal vector there just so it's clear. So if our light source was directly, think of it as being perpendicular to that surface. Well, how bright would you expect that surface to be? How much should it be illuminated? Well, it's kind of like having the sun directly overhead at noon during the day, right? In this scenario, the surface is going to be as bright as it gets, right? It is going to be as directly illuminated as possible with the light source positioned directly overhead, right? This just intuitively makes sense, and you can do this yourself. You can take a flashlight, you can take a light bulb, and just like shine it directly on a surface, and you will simulate this scenario here. Let's take another scenario. I'll actually just copy this surface here and move it over to the side. And in this case, let's consider a light source that is, let's go to another extreme, all right? What if we had a light source right on the surface itself? In fact, just to make that clear, I'm going to move that light source so that it's like sitting right on the surface here. Well, right? Well, if the light source was perfectly on the surface of the object itself, well, how much light would actually be able to reflect off the surface itself? Well, again, this light source would have to be infinitely small. But if it was, then, well, there's not a lot of options here, right? You're going to have light going, perfectly parallel to the surface. And then if it's an omnidirectional light source, you'll have some more light heading out in this direction, and so on and so forth. And well, basically no light rays are able to actually hit the surface of the object and reflect off. It is impossible in this case. All right, so that's another extreme. And let's get another copy of this surface here and just consider something, somewhere in the middle, something not quite as extreme. let's, in this case, consider maybe the light source kind of, maybe somewhere right about here. Maybe at around a 45-degree angle with the surface normal. Put this at 45 degrees. So in this case, how bright would you expect the surface to be? How much should it be illuminated compared to this first scenario where the light source was directly overhead? Well, it should be, it should definitely be illuminated to some extent, but not as bright as in this case right here. But not completely dark either, right? Because some light rays are still hitting the surface of the object. So with these three scenarios in mind, let's start to think, all right, so how can we mathematically determine some useful information here about the position of the light source compared to the surface normal. All right, so hopefully you see what I'm getting at here, right? Take a look at the part of this formula here, right? The normal vector and taking the dot product with the light vector. All right, and I'm going to draw in our light vectors just so it's clear what we're dealing with here. All right, so there's our light vector in this scenario pointing up to the light source. In this other extreme scenario, there is our light vector. Let's just get that on top so that we can see that. And in this case, well, to be accurate here, I should be drawing the light vector from the surface point to the light source, just so we can take these dot products properly. All right, so let's go ahead and take the dot products here. So, well, we know what a dot product gives us. It tells us how similar two vectors are. Are they pointing in a similar direction? So, well, what would the dot product here be between the normal vector and the light vector? Well, they're both pointing in the exact same direction with the light source directly overhead. So that would be a positive, basically the largest possible positive value. Large positive value. All right. Let's take a look at this scenario right here with the light source exactly on the surface of the object, or in other words, perpendicular to the normal vector. Well, what would the dot product be in this case? Well, we already know from our lecture on vectors, and when we talked about the dot product, we know that the dot product between perpendicular vectors is exactly 0. Okay, so all right, we're starting to get somewhere here. It looks like this information is going to be quite useful to us. All right, and let's just finish off the example here by taking the dot product between these two vectors. These vectors, yes, they are pointing in a similar direction. They're not pointing in exactly the same direction, but they're still pointing in a similar direction. The result will be positive, but not quite as large as this example where the light source was directly overhead. So let's call this a smaller positive value. All right. Well, there we have it. Let's just see how this scalar product is being used in the diffuse lighting formula. Well, whatever the result of that dot product is being used to scale the diffuse lighting term. Right. So if the light source is directly overhead, we're basically going to get 100% of our incoming light. If the light source is exactly perpendicular to the surface in question, we will get 0% of that incoming diffuse lighting. And of course, if it's somewhere in between, we're still going to get a positive result here, but we're just going to be, this scalar term here is going to scale down the light intensity due to the fact that the dot product here is a smaller value than it would have been if the light source was directly perpendicular to the face itself. All right, so that hopefully that explains what's going on here with this dot product. And one final thing to note is that you might see this rewritten as the following, right? With D equal to, again, our diffuse coefficient, our diffuse light intensity multiplied not by the dot product between these two vectors, but rather by the cosine of the angle between them. Because of course we've seen in our previous lecture that we can relate the dot product of two vectors to the angle between them using the cosine, right? So this would be another way of writing the diffuse shading term here. And finally, we come to specular shading, which is a little bit different from diffuse shading because we're not concerned here with the position of the light source compared to the normal vector, but rather we are concerned with the view vector and the ideal reflection vector made with the light source. Okay, so just a bit different here. Let's take a look at what this looks like in 3D just to get a bit of an intuition for how specular highlights behave, and then we'll come back and talk about the equation. So back in Blender here, we've got a plane where we can see a nice specular highlight here coming from this light source, again, positioned directly above the surface. And actually, we can move that light source down considerably and just notice the fact that, again, there definitely is diffuse lighting on this surface. It's, it is centered. We can see that quite clearly here, right? The diffuse lighting is just this big bright spot of illumination at the center of the plane. And that illumination, again, using the terminology that I just used a few moments ago, that lighting, that illumination doesn't move around on the surface of the object. It stays put, as you'd expect, right? But the specular highlight that we see right down here, we're going to notice behaves in a very interesting way. And any reflections that we observe in real life do this, right? All you have to do is just walk around, wherever you happen to be, look for bright, shiny highlights, and you'll see them behaving in this exact same way. So it's kind of interesting to note that with reflections, which are inherently different than diffuse shading, they actually move around, or they appear to be positioned at different places on the surface of the object, depending on your view direction or the point of view from which you're viewing the object. So, and I mean, we can see that pretty clearly right here, right? We're observing this surface from, let's call it the left-hand side of the object, and well, there it is. So our specular highlight is at this left corner, bottom left corner of the plane. I can rotate my view around here to the other side, and we can see, well, that specular highlight just moves around with us, and now it's at the lower right-hand side of the plane, right? It doesn't matter where we move our camera, that specular highlight is going to follow us around. And so what we can see here is that, in fact, the specular reflection is based on the view vector, the position of the camera in this case, the virtual camera we're working with, and the ideal reflection vector for this light source in its given position, right? Because of course, in contrast to moving the view vector around, if we instead moved the light vector around, well, of course, the specular highlight also moves in that case as well. So it is related to both the view vector and, again, this ideal reflection vector, which we'll take a look at in just a second. So we'll start off describing our specular reflection calculation in a similar way to the diffuse term that we just took a look at. We're going to see that our specular energy is going to be equal to, again, a specular reflection coefficient. And then we're also going to have the intensity of our light. So our specular light intensity. And then we're going to bring in another dot product here. However, this time it is going to be the dot product between the view vector and the ideal reflection vector. We'll talk about those in a second. And then we're also going to raise this to the power of, let's call it alpha, which is something called the shininess constant. It basically causes the specular intensity to drop off at a nonlinear rate with greater deviations from the ideal reflection angle. Once we draw out a diagram here showing the vectors involved here, that should make a bit more sense. So let's go ahead and do that. Let's draw in a surface again. We'll have our light source somewhere around here. And let's draw a vector coming in to the surface point. So let's grab this color and let's actually draw our camera. How about right here? All right, so let's draw it this way. Let's just put in the normal again, the surface normal of this point that is perpendicular to the surface here. And let's just describe this ideal reflection vector. So the way light works, again, we're not getting into the physics of optics here, but the way light reflects off a surface, there's basically an ideal reflection vector, which is, the angle of this vector to the normal is going to be the same as the angle between the incoming light vector and the normal. All right, so if, let's just say, for the sake of example, if our camera was positioned exactly at the ideal reflection vector, we would be getting the maximum specular light intensity off this surface point. However, we are not positioned at that ideal reflection vector, and instead we have a bit of a deviation from that ideal reflection vector. All right, and so this shows us why the view vector becomes important when talking about specular shading. Remember, with diffuse shading, nothing changed when we moved the position of the camera. That's because the camera's position is not involved in the diffuse shading calculation. It's just the normal vector and the light vector. But with specular shading, look at that. The camera's view vector is involved in the calculation, right? To get this deviation, if there is any, from the ideal reflection vector. And therefore, when we move the camera, or also if we move the light source, but specifically if we move the camera, there will be a change in the position and intensity of our specular highlights. And we can put all of these shading terms together into one big equation, which can be used to create a fairly convincing shading model. And we'll talk about what that model is called in just a second here. But let's just get all these terms in. Let's set I sub p. Let's call that intensity at our surface point. So light intensity at a point. let's set that equal to, and we're gonna introduce in here, we're gonna start by introducing our ambient term. All right, so we can say that our intensity at a certain point is equal to the ambient coefficient times the ambient light intensity. So that'll be our ambient term here, just substituting in that formula. I'll just make that a bit smaller. And then we need to bring in the diffuse and specular shading. So we are going to do a summation here for all the lights in the scene, because we could have more than one light. But the rest of this will just be direct substitutions from the formulas we just looked at. All this summation means is that we're just doing this for every possible light source that we find in the scene. All right, so let's start by bringing in the diffuse shading term here. All right, so again, that will be, just get a different color here. That'll be our diffuse shading coefficient times our diffuse light intensity multiplied by the dot product of normal vector and the light vector. All right, so that substitutes in our diffuse shading term. And to that, we can add our specular term. Okay, one last color here, and just bring in, again, the specular coefficient, the specular shading coefficient times the specular light intensity multiplied by, and remember, it's not normal and light vector. In this case, it's view vector, taking the scalar product between that and the ideal reflection vector, raised to the power of this shininess constant. All right, so that does it for a very simple material model here. This is called the Phong shading model, Phong, named after its creator. And it's actually a very widely used shading model in 3D packages. This is not a physically based shading model. It's more of an approximation of how light behaves, but very fast to use this. This is great for when performance is an issue, and you will see this particular shading model available, as I said, in multiple 3D packages. I just forgot to label this. Let's just label this term just so it's clear. Specular shading. All right, there's our specular term. Okay, so there's the Phong model. That is a great starting point for wrapping our heads around how materials work. The Phong model is a very simple BRDF. And then in the next section, we're going to basically generalize this idea of working with BRDFs and see how we calculate surface illumination in a more general sense. Quick note before we finish this section is that this equation is calculated for red, green, and blue color channels respectively, right? Because we need all of those color channels to construct arbitrary colors. And well, these are all just single dimensional light intensity values. So we will need to do this for each of our color channels to get images in full color.